Okay, let's get started. We have a lot to cover today. I'd like to cover enough such that we can start with branch prediction in the next lecture. Are you guys excited about that? Cool. You'll see different methods for doing black magic in computer architecture. How to predict the branches. But I'll hopefully convince you that there is no black magic involved in it. Except sometimes you can get lucky and predict the branches going the right direction, going in the direction that you predicted it to be. Okay, remember we finished pipelining. Well, we didn't finish. We will never finish pipelining, really. We're going to resolve a lot of issues related to pipelining. But we finished the basic concept of pipelining in the last lecture. And we said that a lot of the fundamental issues in pipelining arise from keeping the pipeline correct, moving, and full, right? And there were several things that hindered the correct movement and full pipeline. And data and control dependencies were two of them. And the third one was what? I thought somebody would complete the sentence. Control dependencies, data dependencies, and resource contention. I guess I went too fast. I shouldn't have said that. But resource contention, right? Today we're going to, we start talking about data dependencies. I'm going to focus a little bit more about data dependencies today, and we're going to jump into control dependencies, which is actually a form of data dependence, but a very special form, because every instruction has a control dependence or data dependence on PC, right? Program counter. We discussed that last time also. But I'll give you a bunch of readings. Some of these I've already given you. I like assigning readings. I think reading is important. This talks about some of the issues that we're going to talk about. This is a good overview. I told you about that. This is actually for the next few lectures. For branch prediction for the next lecture, if you read this one, you will feel that it's less of a black magic than it may first appear to be when you first see branch prediction. But this is a very good technical report from Digital Equipment Corporation Western Research Labs, which doesn't exist anymore. Well, there's a story about that too, but we'll talk about that later. That was written in 1993. It may seem like a long report, but this is one of the best papers to read if you want to understand branch prediction. And it was the state of the art in 1993. A lot has happened since 1993, which I will talk about. And this paper, I wouldn't recommend reading it right now, but this paper puts a lot of things together and discusses a modern, well, relatively modern microprocessor that was built in around 1997 by, again, the Digital Equipment Corporation. It was the Alpha 21264 microprocessor, which was the fastest out-of-order execution engine of its day. And it talks about the pipeline of that engine, as well as a lot of different things that are employed in that engine. So this is a very good reference reading, but I wouldn't recommend you read it right now, but you will read it at some point. Okay? So these are the readings coming up. Everybody's excited about reading papers, right? Or reading in general. Yes, that's good. I'm not assigning you the structure of scientific revolutions yet. Please don't? Okay. Maybe for a different class. Okay, so let's go a little bit more in depth into data dependence handling. I'm going to rush through some of this because this you're going to implement, and this is mainly for your reference in your labs. And a lot of the concepts are basically simple. You need to detect the dependencies somehow and ensure that you obey them, right? The key question is, how do you obey them such that you maintain good performance? And we've discussed this, data forwarding, for example, right? Remember, data dependence types were three. We're going to focus mainly on read after write dependencies, because in our pipeline, write after read and write after write dependencies, these are false dependencies, do not cause a problem as long as you write to a register at the end of the pipeline in program order, right? That's it. We've discussed that before. Whereas flow dependencies are very fundamental. This is necessary for correctness. This second add is reading a register that's written by the first add. Basically, the first add is communicating a value through the register to the second add. Whereas here, there's no value communication that's happening. There's a dependence on a name. You just were unlucky that these happen to reference the same registers. Whereas here, register is really part of the communication abstraction, right? You're really using the register as a communication medium between these two instructions. So you can view computing that way. In that sense, that register file is really nothing other than a medium that facilitates communication between different instructions, right? We'll get back to that. Okay, so we've talked about this already. Flow dependence are more interesting, and we've talked about 5 fundamental ways. I'm not going to go through them again. You can watch the video if you missed the last lecture. That's the good thing about technology, I guess. You detect and wait, detect and forward, and bypass. We're going to look at implementation of this. Detect and eliminate the dependence at the software level. We're going to look at this a little bit also. Predict the needed values. This was value prediction, and execute speculatively and verify, or do something else. We're going to come back to this actually in a little bit more detail when we talk about control dependence, because this is a way of eliminating a lot of the difficult pipeline design issues, doing something else, fine-grained multi-threading. So if you follow the flow dependencies in a pipeline, you see conflicts. What do I mean by that? Here I show you an instruction that writes to register A and a bunch of instructions that read from register A. If this instruction actually moves in the pipeline, it gets the wrong value, because when it's reading its registers, this instruction has not even produced that register yet. Right? It writes to that register only after this write back stage, which means that, and that's true for all of these also, all of these will get the wrong value of RA if the pipeline keeps moving. Right? So, but this one will not get the wrong value, right? Because at this point, when this instruction is in the decode stage, when it's reading its register file, this instruction has already written back. I'm assuming that you're familiar with this basic pipeline that we've been discussing. Okay, fetch, decode, read registers, execute, memory, and write back. At this point, this instruction gets the correct value, but you shouldn't keep the pipeline moving for these instructions, right? So how do we achieve that? I'll just give you some analysis, but this is basically amounts to the fact that you've got to detect the dependencies somehow. So how do you do that? Basically, the key question is, when is there a potential conflict between two data-dependent instructions? We're going to focus on read after write. This depends on the instruction types involved. I'm showing you MIPS over here, but you can do a similar table for any kind of ISA actually. Instruction types and where they are in the pipeline, basically, and how much the distance between them is. For example, if you have a load instruction, it writes to the register file in the write back stage. And if you have another instruction, let's say a branch instruction, that's reading that register in the register file stage, it reads that register in the register file stage. So there's a distance of 3 that needs to be obeyed between these instructions, right? You cannot place that branch instruction, you cannot move that branch instruction until this load writes to the register file. So you can do this, do this chart for every instruction. So when is it safe or unsafe to move the pipeline? Again, let's focus on read after write dependence. You can basically, a little bit more formally, look at the distance between instructions. This is distance between instruction I and J, and where they are in the pipeline. Basically, this could be in stage Y and stage X. If the distance between instructions is less than or equal to distance between the stages, then it's unsafe to keep instruction J moving, right? Because otherwise it'll get the wrong value. Whereas if the distance between instructions, these two instructions, is greater than the distance between the stages, when one writes the register file and when the other one reads, then it's safe to keep the pipeline moving. This amounts to basically, if you're writing to the register file and reading from the register file, there's this 3-stage distance. These instructions should be separated by 3 instructions, right? That's what it means. It could be 3 no-ops, it could be 3 adds that are independent, but you got to have space between them. Does that make sense? So you cannot move the pipeline safely if this doesn't hold. So the key thing in handling data dependencies is, how do you make sure that this holds? Right? If you want to do it in software, you ensure this in software. If you want to do this in hardware, you ensure this in hardware, such that you stall the pipeline until this distance becomes satisfied. You can think of this as a formalizing the data dependencies. Actually, I'm not going to go into this, but if you write these rules, if you will, in hardware, you can actually potentially design CAD tools, computer-aided design tools, that can automatically design a pipeline for you. Because what you're really doing is there are some constraints you need to satisfy in terms of the correct movement of the pipeline. And you know all the instruction types, when they write to the register, when they read from a register, and you know what's the safe distance. you can actually formalize all of this and input to a program, and that program perhaps can generate the interlocking logic that's needed to satisfy this constraint. Right. Now, you're going to probably not do that in your assignment. You're going to probably do it manually, but you can imagine a tool doing this for you as long as you formalize the constraints that are needed to ensure that the pipeline moves correctly. Right. And there's a whole field, computer-aided design, that tries to do that. Have you guys looked at any of computer-aided design tools? Okay. You may have used some of that in 240, actually. SIS, for example. Or maybe, does that sound familiar? Okay. Anyway, maybe we'll look at it when I teach 240. Okay. Well, let's ignore these for now, because in our pipeline, there's no issue with right after read and right after write dependencies. But again, over there, you need to satisfy the distances. You can imagine it that way. Okay. So let's take a look at this analysis. Basically, instructions IA and IB, where IA comes before IB, have read after write dependence if IB, one of these instructions, reads a register written by IA, right? And the distance between IA and IB is less than or equal to the distance between when IA reads the register and when IB writes the register. And in our pipeline, it's 3, basically. Ignore this one. Okay, so that's how you can detect the data dependence, right? Basically, well, let's assume that you somehow detect it. How do you fix the problem? Well, how do you fix the problem? Let's say you have instruction I and J over here. And their distance is really 1, right, in the program. Which means that they do have a data dependence, because one is, I is writing to a register, J is reading from. How do you make sure the pipeline moves correctly? Well, basically you insert bubbles such that the distance becomes 3. Right? I guess in this case it became 4, right? Well, yeah, it becomes greater than 3, right? Yes. Does that make sense? You could imagine hardware doing this. In this case, hardware is injecting the bubbles, hardware-based interlocking, or software inserting knobs, right? That's software-based interlocking. Hopefully with software, perhaps you can do better, right? Maybe you can find independent instructions somewhere else and insert them over here. Make sense? So that formalization actually helps the software also. Compilers can benefit from that formalization. Okay, so what is a stall? Basically, I told you before, stall means making the dependent instruction wait until its source data value is available. It means that you stop all upstream stages, upstream meaning later instructions, including this instruction that's dependent on an earlier instruction, and you drain all downstream stages until this distance is satisfied. And you need to have control in the pipeline, yes?
By upstream, don't you mean the earlier instruction?
Well, earlier in the pipeline, but later in terms of program order.
Oh, okay.
Yes. That's right. We've got to be careful with the terminology. Younger instructions. I like younger better. Younger instructions. Whereas older instructions should go because they've been fetched earlier. Okay. So how do you implement stalling? This is the pipeline that you're going to love more over time. But basically, how do you ensure that the earlier instructions do not move? Let's say we're going to implement stalling here in this stage because you're reading the registers over here. How do you make sure that the earlier instructions don't move? Well, you'd better not latch the program counter. You'd better not latch anything to this instruction register, right? Basically, don't fetch the next instruction. And this instruction essentially stays in this stage in that case. So, but you should ensure that the rest of the pipeline is moving such that those instructions can generate their results. But what happens to this pipeline register in the next cycle if you're injecting a bubble? Basically, you insert invalid instructions or no ops into the stage following the stalled one. This is the stalled stage because you're reading the registers, which is not available, which means that when it's stalling, it should inject a no op in the next stage. That's the bubble. And you could do this in multiple ways. I mentioned the valid bits, right, in the previous lecture. You can have a valid bit associated with each of these pipeline registers. And if the valid bit is set to 1, that means this pipeline register is a bubble. Don't do anything. And everything that does harm, that updates state, is gated with that valid bit. That's one way of doing it. Or you can set the control signals such that they indicate a no op, right? That way you don't have the valid bits. Okay? It's fun. So basically, stall conditions, we've discussed this before. Basically, you must stall when instruction B that's dependent, instruction B is in ID stage, decode stage, wants to read a register to be written by instruction A in execute memory or write back stages. And how can you determine that? Well, this is one way of designing the hardware to determine that. I'm not going to go through this in detail, but you can imagine. This is a simple concept, right? Basically, if the destination register in the EX, MEM, or write back stages matches the source register, any of the source registers for the instruction decode stage, and the instruction decode stage actually wants to use that source register, right? And the instruction in the execute memory or write back stages are respectively writing to a register, any of them, then you need to stall. This is the hardwired logic, right? This is not the scoreboard. Remember we mentioned how do you actually implement interlocking? Scoreboard was one way. You have a val bit per register. This is the combinational logic to achieve the same effect. Well, we've already talked about this. If you don't advance execute memory and write back while you're stalling, then you've deadlocked the machine, right? Okay, so there's obviously some impact of stall on performance, right? Ideally, we would like to have, if you have a one-wide pipeline, meaning 1 instructions per cycle, you would like to achieve the 1 instructions per cycle throughput out of the pipeline, right? You'd like to complete 1 instructions every cycle. Make sense? Whereas if you stall, you're basically losing 1 cycle in which no instruction can be completed. You're injecting a bubble, right? And that bubble propagates through the end of the pipeline, and you have a write-back cycle where you complete no instruction. This does impact performance. And a lot of the pipeline, a lot of the techniques we will see will try to reduce the effect of this stalls on performance. So this is a very basic equation. If you have n instructions in your program and s stall cycles, ideal throughput is n over n, right? Whereas every stall cycle takes away from your throughput. So cycles per instruction becomes m plus s divided by n. Or throughput becomes n divided by m plus s cycles, right? N instructions divided by m plus s cycles. So ideally, you would like to minimize s. So s will be actually depend on many things, but in terms of data dependencies, in terms of read after write dependencies, it depends on how frequently do you see read after write dependencies, right? What is the exact distance between the dependent instructions? So there may be a read after write dependence between instructions, but that may not lead to a stall because instructions are far away from each other, right? And distance between dependencies also. So let's take a look at that. So a lot of the techniques we will see will try to minimize s. So if you have a memory stall, for example, if you're waiting for memory for hundreds of cycles, you can imagine that average CPI increasing significantly. Okay, this is one sample assembly from Patterson and Hennessy, and it consists of, well, this is a mess that's done in some programs. You can imagine why this could be done, but I'm sure you've written programs that look like this or worse. I have. But basically, this is the assembly for this program, and you see a lot of dependent instructions. For example, this shift is dependent on this add, and this branch is dependent on this shift, and a lot of dependencies. Basically, if you have this code this way, and you have the same pipeline that we've discussed, you get pretty much 3 stalls every third, basically 2 times 3, two sets of 3 stall cycles every third instruction, right? Well, I didn't put it that way. Basically, count the stall cycles over here. You have to stall for 3 cycles over here. You have to stall for 3 cycles here. Here, there's no dependence, so you can execute them back to back. Here, you have to stall for 3 cycles, stall for 3 cycles. Here, you can execute them back to back because they're totally independent of each other, these loads. Again, 3 cycles, 3 cycles. Those look terrible, right? You have a pipeline, but you're pretty much all the time stalling 3 cycles just to satisfy data dependence. Right? Okay, so data forwarding fixes this program at least most of it. Right? So let's get any questions so far? This is all simple, right? You can implement the data dependence shaking logic in your pipeline now. If I ask you right now, you can do it. I'm not going to ask you, but you'll do it anyway for your lab. Okay, so it's intuitive to think of our register file as state, right? I told you earlier at the beginning of the lecture. register file is really state. Basically, this means that get values from register file location ry and rz and put the result in rx. But it's really a communication abstraction, right? Registers are used to communicate between instructions. If you think of it that way, you may not even want registers. Data flow, for example. Remember the data flow model that we've discussed in one of the earliest lectures? You don't really need registers there. You just need arcs, meaning an instruction specifies who is the destination, which other instruction should get this value, right? So we're going to do something similar in the pipeline to communicate between instructions without going through the register file. And that's the idea of data forwarding. Basically, if an instruction needs the value that's produced later on, don't just wait until that value goes into the register file, but provide paths or buses in the pipeline such that that instruction gets that value right after it's produced. That way, that instruction doesn't need to stall, right? And we're going to look at an implementation of this. Well, I guess you can read this in your spare time. But basically, okay, let me read it. This you can interpret this instruction as not going through a state, but this add means get the results of the last instructions to define the values of these locations, just these values. They don't have to be in the register file. And until another instruction redefines the destination location, younger instructions that refer to Rx should use this instruction's result. Basically, this is an instruction viewed as receiving values and communicating values, just like in data flow. Basically, what matters is to maintain the correct data flow or correct value communication between different operations. Register file, whether or not you get the value from the register file doesn't matter. Register file is just an abstraction where that value happens to be stored. As long as you have the value available somewhere in the pipeline, you can supply it. You have a question? Okay. Okay. So, which means that the value of this add is actually available right after the end of this execute cycle, right? We've computed the add happens in the execute cycle in the ALU. There's no reason to wait 2 more cycles until this add writes back its result such that it's communicated to this instruction that's dependent. So data forwarding or value communication does this. You add logic to the pipeline such that you don't wait unnecessarily, but once the result is available, you supply it to the next instruction. That way, well, there's no stall anymore, right? These are back-to-back dependent instructions. This instruction produces its result, and this instruction captures that result through the bypass or forwarding path, and it doesn't stall at all. It just ignores the value in the register file. Right? That's the idea of data forwarding. So what does this mean from a little bit more formal point of view? We know that this is the dependence. But if an instruction B in stage ID, instruction decode, reads a register that's written by instruction A in execute, memory, or write-back stages, then the operand required by IB is not in register file yet. Right? We know that. And data forwarding says, retrieve the operand from data path instead of the register file, and have some path for that. And of course, there's a second thing. Retrieve the operand from the youngest definition if multiple definitions are outstanding. What does this mean? If multiple instructions are actually writing to the same register, pick the youngest one, right? You don't want to pick the oldest one, then you get the wrong value. Does that make sense? Okay, excellent. So how do you actually implement this? And I believe you'll implement this also in your pipeline. But where's the forwarding? Okay, there you go. There's some forwarding unit here. Basically, we need to add some forwarding paths. You can forward the result coming from the ALU. Well, this is the ALU result. That gets forwarded to the input of this MUX. So the value can come from the register file. The value can come from the ALU. The value can come from the memory stage. Or the value can come from the write-back stage. Right? Basically, you add these MUXes. These MUXes enable forwarding from later stages. Whereas before, if you didn't have forwarding, the only place values can be read would be the registers, right? But now you can get the values from the ALU results. You can get the values from the data memory. You can get the values from the write-back stage. Does that make sense? Well, the downside is now you need to add all of these muxes, right? Because your values can come from not only registers but other places too. And of course, the control for the muxes. What is the control for the muxes? Well, very similar control as what we've discussed. If this instruction is reading, well, I'll show you actually in a little bit. And actually, you'll design this. Does that make sense? So you can, everything's a trade-off. So upside is now hopefully your cycles per instruction reduces because you don't need to wait until the value is available in the write back stage. But maybe you've lengthened the pipeline stages. But you've lengthened your clock cycle, right? Maybe. It's not clear. Because you've added these muxes. These muxes didn't need to be present. This is the trade-off between cycles per instruction and clock cycle time. You may do something that gets your cycles per instruction to be lower, but your clock cycle time may increase. So this is where the forwarding happens if the instructions have a distance of 1. This is where the forwarding happens if the instructions have a distance of 2. And this is where the forwarding happens if the instructions have a distance of 3. Yes?
So doesn't it need to wait until all the other stages are finished before it can bring it back to that stage?
What do you mean? All the other stages are finished.
Yeah.
Let's assume that you have an add that's writing to a register and another add right after that that's reading. Mm-hmm. As long as the value is available.
Yeah, but I mean in one clock.
Absolutely, yes. In one clock, yeah. This all needs to happen in one clock.
So it's it's going to guarantee to be longer than the other 3 after it, right? Because it has to do the muxes after those values come in.
Yes, that's right. Well, basically, your critical path is a little bit tougher right now because it could be this data path, or it could be its control path, or it could be any other data path going into the mux, right? So you need to figure that out and ensure that this works correctly. You're absolutely right. That's another place where the critical path increases, and you have a loop right now in the pipeline, right? Now pipeline stages are kind of dependent on each other, and you need to ensure that this works. Okay? And that's true for, and I'll show you for that reason another potential design, that's why I have version 1 over there. Version 2 is, here in version 1, muxes are before the registers, before the pipeline registers. These are pipeline registers. In version 2, we're going to put all of the muxes after. Before I go there, I forgot that this could be one forwarding path, but the other forwarding path could be, if your register file works this way, in the earlier part of the clock cycle, you can write to the register file, and the later part of the clock cycle, you can read from your register file that written value. If your register file works that way, then you can do an internal forward in the register file. Make sense? That's an internal forwarding path. That way, you get rid of one of the inputs in your mux. Okay, this is the version 2. Now, the muxes are not at the end of a stage, but at the beginning of a stage. You could do the same thing. And if you have a distance 1 instruction, basically, if you have 2 instructions that are dependent on each other and their distance is 1, this is the forwarding path they would take. For instructions that have a distance of 2, this is the forwarding path they would use. And internal path that I discussed is the third path for instructions with a distance of 3. Well, which design is better? It really depends on your critical path. It's hard to tell, right? Here, if your critical path is your register file, and maybe here, it may not be a good idea to have that. If here, your register file is not on the critical path, right? You don't add much to your register file because the muxes are gone from here, muxes are moved here. It really depends on which one's your critical path. Okay? Any questions? This is fun, right? Wait until we get to out-of-order execution. There, you will really do the value communication. Everything will be based on values. Like data flow, right? Okay, so let's assume this version 2, because it's a little bit cleaner, because I don't have this other path here. Basically, what's the data forwarding logic? It's simple now. Basically, you have special cases for distance 1, distance 2, and distance 3 instructions. And you got to prioritize, right? If an instruction is writing, if an instruction is writing to the same register and the distance is 1, you'd better get that value, as opposed to an instruction that's writing to the same register and you're trying to read it and the distance is 2, right? And you may have multiple instructions writing to the same register. So basically, if the source register is not 0, because source register is 0 and MIPS is actually tied to 0 values, then there's no dependence basically. If the source register that's being read in execute stage is not 0, and the source register in execute stage is equal to the destination register of the instruction in the mem stage, and the mem stage instruction is writing to the register that control signal says, then forward the operand from the mem stage. That covers the distance 1 case. Basically, it's this. If those conditions are true, this input of the mux is selected. Make sense? Else, if it's not 0, if the destination register is, source register is not 0, and source register of the execute stage is equal to destination register of the write back stage, and the write back stage is actually supposed to write to a register, then forward the operand from the write back stage. Otherwise, use the operand from the register file, because we assume a register file internal forward for a distance of 3. It's actually simple control logic, right? But this control logic obviously gets larger and larger as the number of pipeline stages increases. Right? Okay, ordering obviously matters. Yeah. Why doesn't use RS appear in the forwarding logic? Basically, we're not checking whether the instruction in the execute stage is actually using the source register. That doesn't matter, right? If it's not using the source register, the value will be supplied. You select some value, but you'll discard it. You won't do anything with it. Right? That's the reason. There's also one thing over here. What is the above does not take into account? Yes?
If you're writing to memory, which you can also do a loopback for.
That's a good one. That's not what I was thinking about here, but you're right. How do you handle memory dependencies, right? How do you have a store versus load?
So like you could compare the addresses.
That's right.
Bypass the cache and memory.
That's right. You could potentially do that. In this case, actually, it won't matter because everything happens in order, right? Store, load, because you're storing to memory and you're loading from that memory location, and they all happen in order over here.
Okay, yeah, that's true.
But there are actually pipelines, and we will discuss this when we get to out-of-order execution. That is a real issue in out-of-order execution, because you may have a store instruction writing to a location, and you may have a younger load instruction reading from that location, and you may not know their addresses yet. But we'll get to that. There's one thing this doesn't take into account, which is the valid bits. Basically, you don't want to, if the instruction is not valid in any stage, and if you're actually using valid bits to ensure bubbling in the pipeline, stalling in the pipeline, then you need to look at the valid bits of the destination registers, right? Valid bits of the instructions that are in the mem stage and in the write back stage. Because if they're not valid, for example, let's say you have an instruction that's writing to R2 in the mem stage, R2 in the write back stage, and the instruction in the execute stage is reading from R2, then normally you would forward from here. But what if this instruction is not valid? Right? You don't want to forward that. Then you'll get the wrong value. Remember the valid bits, if you're doing pipeline control with valid bits, you really need to check the valid bits everywhere pretty much. You don't want to supply the value that's not valid. Does that make sense? Okay. Okay, maybe I should go faster. Everybody says this is good. This makes sense. Yes?
You could fix that also by just not loading the register, right? So if you don't load the boundary registers, you have the same values, and you can just not take that into account.
That's right. Basically, if your register write signal is 0, right? That's what you mean? Yes?
No.
No? Okay.
Like you didn't write, and essentially you didn't write a bubble in.
Uh-huh.
Oh no, but you still have to keep.
Exactly. You need to either turn it into a no-op, which means that the register write signal becomes 0 over there and it's automatically taken care of, or have a valid bit saying 0 and then take that into account in this logic. Okay, so now let's take a look at the dependence analysis with data forwarding. Now we don't have register file write and register file read anymore. What really matters is when an instruction produces a result and when another instruction uses the result. And if you look at our pipeline and different types of instructions, For operate instructions, R or I type instructions, they produce the result at the end of the execute stage, and they use the result at the beginning of the execute stage. So their distance is really 0, right? Well, basically, you can provide a forwarding path from the end of the execute stage to the beginning of the execute stage. And what we did was from the beginning of the memory stage to the beginning of the execute stage, such that you don't need to stall at all if you have R-type instructions in the pipeline. But if you look at a load instruction, it's not that way, right? Load instruction actually produces its result at the end of the memory stage. And if you have an execute instruction that uses the result at the beginning of the execute stage, well, the distance must be 1, right? Distance must be greater than 1, actually, for the pipeline to move correctly. So you cannot forward this value. There's nothing you can do. Let's take a look if this is not clear. Basically, load instruction, well, what happened here? Yeah. Load instruction produced its results over here, right? And you have another instruction that needs that result. Well, too bad. You cannot forward that result, right? Unless you really, really lengthen the clock cycle somehow. Does that make sense? OK. So let's say what happened to our pipeline, to our program, the sample assembly program. We had lots of stalls because we didn't forward any values. Data forwarding actually eliminates all of those stalls, except for this one. Here the load is writing to a register, and the shift actually needs that register. Make sense? Everybody understood that why the shift cannot get that register in the next cycle, right? You need to insert a no-op or a stall here. Because it's too late. By the time this load produces that result, it's too late. If you move the shift over here, shift is computing while load is accessing memory, right? So by the time the load is done and latched its result, shift has already moved here. You cannot forward that value. So you should stop shift from moving here while the load is accessing memory. And when the load is done, the shift can move here. But at that point, there's a one-cycle bubble in the pipeline. OK? So that's the problem with loads, actually, because they go through extra stages. And they lead to a lot of stalls. And we'll see that the problem is actually much worse than that with loads later on. OK. Any questions? Good. Wow. We're not really on time, but we can go faster. Am I going too fast? Yes. No? Who says yes? Don't be afraid. That's good. A little bit. Who says no? Nobody. Everybody's afraid of no. you were like this.
I think you were proceeding aggressively.
Okay. Well, yeah. Stop me if it's. Yeah. Stop me if anything is not clear. Everybody understood the concepts now, right? Data forwarding, how you would implement it. You really will know when you implement it. That's why we have a lab. I can tell you over here, I can draw the logic. It'll be not the best use of our time. The best use of your time is really go and implement it and figure it out on your own. That's actually the best way of learning this. Yes?
So the problem, to answer that question, was like the load operation that didn't take into account.
Say it again?
The answer to that question was the load operation isn't taken into account, basically.
Which one?
The one on the bottom, like, yeah,
Oh.
What did it not take into account?
So this doesn't take into account the valid bits, right?
Oh, okay.
Yeah, this doesn't take into account whether the instruction that's actually producing the value in the mem stage is valid or not. And you need to check that, assuming you have a valid bit-based implementation. If you inject bubbles into the pipeline by ensuring that the instructions in the later stages are no-ops, then you don't need to take into account the valid bits. Because that way, when you inject the bubble, you ensure that this reg-write signal is 0. Right? Again, you'll learn this better when you implement it. OK. I don't think I'm going to go through this a lot, but I'll just show you something. Because you're not going to do this for your lab. But this could give you ideas for the design of your lab. But I guess it would be too much for you, too much for me to ask you to do this as well as your lab. But I'll give you some ideas on how you can pipeline the LC3B. Remember, we had the single bus data path, right? So we're going to divide into 5 stages, and this will be a good document that you can refer to. Fetch, decode, RF access, address generation, execute, memory, and store result. Very similar to the MIPS pipeline. And we're going to assume conservative handling of data and control dependencies. Stall on branch, stall on flow dependence. This was the single cycle data path. Well, this is the pipelined version of it. Actually, we had designed this in 2003, and it still looks like this. When I was TAing a similar course at the University of Texas, this was kind of my baby assignment for students to learn pipelining, and I'm still proud of it. It looks kind of nice, right? But basically, this is what the pipeline looks like. It's a valid bit-based design, and you have the fetch stage, and you have the decode stage, and you see the control signals are delineated over here. You have the address generation execute stage, memory stage, branch condition determination logic, and write back stage, or store result as we called it at that time. And control signals are growing less and less as you move through the pipeline. And this is what fetch stage looks like. I'm not going to go through this, but if you would like to learn, you can read the handout. But this is what I mentioned with the valid bit, for example. And it'll be your job to figure out what this logic is if this were an assignment for you. But you'll do it for other implementations. Basically, somehow you need to decide whether you actually load the decode register and whether you make it valid or not. Right? And this is the dependency check logic. This basically determines whether you should stall the pipeline or not. Remember, this doesn't have forwarding. I said it's a conservative implementation. You stall on flow dependence. Basically, this dependency check logic checks whether any instruction that's later, this is the decode and register file access stage, whether any instruction later in the pipeline is, let's see, writing to the register, whether the destination register ID is same as the source register ID of this register in this stage, any of the source register IDs, and the instruction in a later stage is valid. If that's the case, and if this instruction needs source register 1 and source register 2, so you have this combination of logic that detects that dependence, basically. Okay? Okay, I guess I'll keep moving over here. But you can basically read the handout. Let me talk about a little bit of the control, because control is actually a little bit different, because you have data path control signals, which control the operation of the data path. You have control store signals. These are micro instructions stored in the control store to be used in the pipeline data path. They can be propagated to stage later than decode. This is very similar to microprogram control, except you propagate the control signals. But you also have stall signals. And these signals are new. They're different from the microprogram version, right? These ensure the pipeline operates correctly in the presence of dependencies. And you could do the same exercise we did for the microprogrammed LC3B, and you could actually add the new control signals. This is a listing of all of the control signals in the pipeline. And this is what you get from the control store. And control store can actually provide the signals that are going to be used in different stages. And these are the different stages where the signals are needed. Make sense? Okay. Okay, I'll skip this also, because these are things that we've actually talked about. Like, why do you need to stall, for example? Hopefully you all know why you need to stall by now, right? Okay. Some questions to ponder. I don't think I'm going to answer all of these questions, but these may be good to think about. What is the role of the hardware versus software in data dependence handling? You could do software-based interlocking. MIPS, their original intent was designing a microprocessor without interlocking pipeline stages, where software interlocks, meaning software ensures that the distance between instructions is greater than some value such that data dependencies don't cause a problem in the pipeline. You could do hardware-based interlocking, and we've examined this today a lot. Who inserts and manages the pipeline bubbles? Well, if you do software-based interlocking, there's no need to do that, right? Well, except for memory operations. What if you have a 500 cycle memory operation? Can the compiler insert 500 instructions or 500 no-ops after that? Well, does the compiler even know, right? Because we're going to cover the concept of caching. If you get a cache hit, the memory operation takes 3 cycles, let's say. or 1 cycle, let's say. If you get a cache miss, the memory operation takes 200 cycles. How does the compiler account for that to do software-based interlocking? It's a bit tough, right? The compiler can always assume the worst case, can assume that the load instruction will always miss in the cache. But that's a terrible case. That means that the compiler always injects 200 no-ops. Well, maybe a couple of independent instructions and then no-ops. Because it's hard to find independent instructions, as we will discuss soon. So think about these issues. Software-based interlocking, pure software-based interlocking is very tough. You have to have somehow a signal that says, oh, this thing is not ready. Don't move the pipeline, right? And where you really, really, really need that is when you have a memory operation, right? When you fetch the instruction, if the instruction, well, fetch is easy, I guess. You really need to have that in fetch, right? You shouldn't move the pipeline if the instruction you fetched misses in the cache, right? If you cannot even fetch the instruction, then the pipeline you should be injecting bubbles. So you have to have mechanisms in hardware to inject pipeline bubbles. So you could actually combine these two also. Compiler can do the best it can, and the hardware can do the best it can as well to get the best of both worlds. And we will probably get back to that. The other question this implicitly asks is, who finds the independent instructions to fill empty pipeline slots? Well, if you do software-based interlocking, the answer is obvious, right? The compiler or the programmer somehow figures out independent instructions such that you don't need to stall. Right? What about hardware-based interlocking? In the solutions that we've discussed, the hardware doesn't reorder instructions, right? But we'll see that the hardware can actually reorder instructions to actually fill those bubbles, if you will, otherwise bubble cycles. That's the idea of out-of-order execution. The hardware looks ahead in the instruction stream, tries to figure out what is independent, and tries to schedule that instruction such that it can be executed, such that you don't get a stall. Does that make sense? Okay. And I think I'm not going to cover this, but this is for questions for you to ponder. What are the advantages and disadvantages of each? Software-based interlocking versus hardware-based interlocking, and the answer to these questions also. Well, the upside, if you can do pure software-based interlocking or mostly software-based interlocking, the upside is hardware is simple, again, right? The downside is the burden is on the software now, compiler, programmer. There's another downside with software-based interlocking, actually. Can anyone think of that? Yes?
That it's not dynamic. So kind of like what you got at with memory.
That's right.
Software has to assume worst case, whereas hardware can know and figure out what the best dynamic bubble insertion.
That's right. Exactly. Yes, it's not dynamic. So because software doesn't have complete information about what's happening during execution. Because software compiles the program before it runs, and while the program runs, the latency of an instruction may be different, right? The software can assume that the load instruction always misses in the cache and schedules the code that way, whereas in reality the instruction may always hit in the cache. And that way you have a terrible schedule in the software. Yes, go ahead.
Program size is also much larger,
Mhm.
so they have to keep inserting no-ops everywhere.
That's right. Assuming you cannot find independent instructions, your program size becomes larger. This is good. These were some of the things that it's always good to think about the advantages and the disadvantages of different approaches. Yes?
Well, couldn't you get around that problem?
Which one?
Of loads you don't know how long they're actually going to take if the ISA gives the compiler an instruction to say, if it's a miss, do this. If it's not a miss, do this.
That's right.
There's a number of no-ops inserted or something like that.
That's a good question, actually. So basically now you're modifying the specification of the load instruction. Basically, you're exposing this hit-miss signal to the software, and the software takes a different action. Basically, load is now a branch, if you will. If your load hits in the cache, execute the sequence of instructions after that. If your load misses in the cache, execute the sequence of instructions after that. I like that idea. It's not done in today's processors. People have proposed that idea as research idea, actually. It complicates the load, certainly. Because you fetch the load, now you need to predict what set of instructions to fetch depending on whether or not the load will be a hit or a miss, right? Now your load is a becomes a control flow instruction. I like the idea, though. That's a very interesting idea. So that can actually enable the software to generate code for different conditions. Yes?
Well, one way you can kind of mitigate that but still keep code size is by having a no-op that has the address of the next non-no-op instruction.
Uh-huh.
So essentially the processor will keep executing no-ops, and when internally it knows that memory has been loaded, it reads the offset address in the no-op instruction and
I see.
then jumps to that.
That's right. That way you get rid of some of the code size issues.
No,
Right.
you would still have the same code size, because you would have all the worst case no-ops.
Uh-huh.
But performance-wise, once the hardware knows it fetched something from memory, it can jump to the next instruction because that next instruction is encoded. The address is encoded in the no-op.
Okay.
Well, why wouldn't you just have a no-op that, instead of having a no-op that knows to branch somewhere, why wouldn't you just have a no-op that knows to repeat itself
That's
however
right.
many times and then branch?
Yeah, you could do that
You
too.
do a repeat no-op.
Yeah, exactly. Yeah, you could do a repeat no-op in x86. Now you're trying to solve some of the problems with it.
Yeah.
But you still need to, all of these solutions have issues, basically, as we've discussed, right? Yes, you have another solution.
Software-based interlocking, would that mean you would have to assume a particular implementation of the microarchitecture?
Exactly. This is actually one of the things I was thinking about when I said, but you found out another shortcoming. Basically, software-based interlocking, you really need to know the implementation of the microarchitecture. If your pipeline, if your pipeline stage is 5 cycles versus 7 cycles, requires different kind of code, right? That's a big downside. Now you're tying the implementation to the, not exactly ISA, but you need to basically generate code for new architectures every time. You lost backward compatibility. Or to maintain backward compatibility, you really need to be very, very careful when you're designing your next implementation, right? Which is very difficult, actually. So that's another downside of software-based interlocking. Software needs to know the underlying implementation. But this is a very, very classic trade-off that we've been discussing, right? If you punt a lot to software, the software needs to know a lot underneath. Right? This is the open microcode, for example. Right? If the software needs to generate all of the control signals, the software obviously needs to know every single implementation detail. Right? Okay. These are great things to discuss, actually. I'm glad you guys are generating some ideas. I had something else to say related to this, but okay, maybe it'll come to me at some point. Oh, yeah. This is what I want to say, actually. There are some solutions, but there are still some other solutions. So software, even though it may not know what happens dynamically for a load instruction, it may guess, right? So the software, for example, can say, oh, this load instruction that I see over here, I'm going to guess that it's going to mostly hit in the cache. And it can optimize the code that way. Right. Now the downside of it is, if it misses in the cache, you still need to have hardware-based interlocking to handle that case. That's fine. But software has another option to optimize the code, just to optimize the code. And that idea is basically somehow guessing. Right. It's very similar to what we will do in hardware. How can the software guess? Any ideas? You have a load instruction. Yes?
I could use locality. So like if you're iterating through a memory array,
Mhm.
you can assume that it's in the cache.
That's right. So software can do some analysis of the program, for example, and can say, oh, this load is always referencing the same, let me make it more extreme, always referencing the same address. That happens to be used a lot. So I'm going to guess that this is going to be in the cache most of the time. I'm going to say this load is actually hid in the cache. So I'm going to schedule the instructions assuming that. And there could be some cases like that. Or if you have good locality, and we'll talk about that later on. What if it doesn't know that? It cannot figure that out by analyzing the code. What else can the software do? A compiler has actually a lot of time to optimize a program. Think about it that way. It can do a lot of things with the program. It can run the program. Right? Yeah, it can run the program, right? It can say, let me run this program. Let me figure out for a bunch of different inputs, for a bunch of different arrays that are input to this program, let's say, what happens to this load? Let me run it 20 times, 30 times. with 30 different inputs. Maybe the programmer tells me, I'm going to run this program. Let's say you're doing a dictionary lookup, for example, and you give it a bunch of words as inputs. And the software can run it and say, oh, in most of the runs, most of the executions of this load, it hid in the cache. It can profile. That's the idea of profiling. Or static or compile time profiling. Basically, the compiler can run the code with potentially representative input sets, and I'll define this, or input sets, and check how many of the in how many of the executions of this load did this load take 3 cycles versus 200 cycles? Right? Did it hit in the cache versus miss in the cache? And if an overwhelmingly large fraction hits in the cache, then the software can say, oh, I trust these input sets, I profiled the code, I ran it with these input sets, so I'm going to assume that it's going to hit in the cache for the input sets that will be used when the program actually runs. Yes?
Does the ISA give you tools to be able to do that profiling? Because I imagine adding code to the code that you're trying to profile would inherently change the
That's
results
right.
that you're getting.
So that's right. Some ISAs actually give tools for that, but in many cases you add code, instrument the program to do actually that profiling. We'll talk about this when we get to static instruction scheduling a little bit more. But this is the idea of profiling, and basically the compiler can use this to optimize the program, right? To learn information about the program. The downside, well, the upside is now you can guess. This gives you the ability to guess. And if you're correct in your guess, you optimize the code nicely. The downside is this. How do you get representative input data sets? Let's say you're Google, you're optimizing your search engine code. And how do you optimize that? Maybe you have some representative queries, right, that the users have. Maybe most people search for something in particular, right?
Super Bowl.
Yeah, exactly. Maybe those representative queries are dependent on time, right? Maybe based on time you deploy different kinds of code, right? Exactly. So that's a representative input set today, perhaps, right? If you optimize your code based on the input set Super Bowl, maybe that runs much faster, right? But if you search for totally something different, computer architecture, hopefully that's not the worst, then you get a slower code because you've optimized the code for Super Bowl. Right? So that's the idea. The key to be successful in profiling, static profiling, is to come up with representative input sets. How similar is the execution of the real run of the program to the execution of the profile run of the program? And that is dependent on the input data set. Okay? Okay. I think we've covered a lot in this slide. Well, actually, this will come again. So what is the role of the hardware versus the software in the order in which instructions are executed in the pipeline? Basically, we've talked about this. Software-based instruction scheduling, static scheduling. Hardware-based instruction scheduling, dynamic scheduling. We'll talk about that. Static scheduling, in static scheduling, compiler orders the instructions. And the hardware executes them in that order, obeys that order. Right. Well, assuming a von Neumann model, hardware always obeys that order from the point of view of the programmer. But internally, it may be different, right? But in pure static scheduling, internally, hardware obeys that order also. But dynamic scheduling, in dynamic scheduling, hardware will execute instructions out of the compiler specified order. And we'll take a look at that. I think we've covered a lot of this. So if you want to do pure static scheduling, compiler somehow needs to know the latency of each instruction, right? Which means that you need to expose those latencies. But there are some latencies that the compiler doesn't know, and one of them is the load latency, right? Load hit miss latency. Well, how long a load will take? It could hit in the cache, miss in the cache. It doesn't know. Basically, anything that's not determined at runtime. One of you said dynamic information, right? The compiler doesn't know. What are these things? Variable length operation latency is one. There are 3 things actually. One is, I like to think of it as variable length operation latency. this compiler doesn't know how long the load will take. There are other variable length operations. For example, you can have a hardware design that takes different amount of time for this instruction. One execution of this instruction takes 1 cycle, another execution takes 20 cycles. Why could that be? Yes?
Maybe it just keeps adding for multiplication. So if you multiply
Uh-huh.
a number by 1, it's just
Oh, exactly. Yes, that's right. Basically, what you're saying is it's really dependent on the data value, right? If this data value is, if all of the data values are not 0 or not 1, you basically take 24 cycles. But if any of the data values is 0 or 1, you can do it in 1 cycle, right? That's another example where the compiler may not know, and usually does not know the value in the registers. And as a result, the operation is variable length, variable latency. Memory address is another thing compiler usually doesn't know, because memory address is determined dynamically. And we will see that this causes problems when the compiler needs to reorder instructions, right? Because the compiler you may have a store instruction over here, and you may have a load instruction over here, right? And there's some address computation for the store. Well, I guess R5 gets stored to this address. And there's some address computation for the load. The compiler may have no idea what's the address of the load versus the address of the store. But the compiler may want to put this load earlier such that it can, because this load may take longer, right? It can overlap the latency of the load with other instructions. But because it doesn't know the address of the store, this movement may not be safe, right? Because if the load is actually loading from the same address that the store is writing to, the compiler should not move this, because there is a dependence between the store and the load. Again, how does the compiler figure it out? Well, profiling would be nice, right? But profiling does not always guarantee correctness. Profiling just tells you for these input sets, these stores and load, the store and load may or is dependent or is independent. But there may be some other input set where these are dependent. So this is a difficulty for the compiler in reordering code. And the last one is branch direction. Well, branch direction also matters, and we will see this again. But let's say you have a branch here, and based on the branch, you execute this piece of code if the branch is taken. If the branch is not taken, you execute this piece of code. And what the compiler, because the compiler doesn't know which direction the branch will go, it may be difficult to optimize the code, right? Because what the compiler might want to do, again, is you have a load instruction over here. It may want to move this load instruction up here, right? Such that its latency is overlapped. But this may again be a not safe movement because there is a branch here. This load instruction is executed only if the branch is not taken. There may not be the same load instruction over here. And compiler doesn't know if this branch is taken or not, so this movement can be unsafe. Can lead to incorrect results, actually. So the lack of this dynamic information hurts the compiler a lot. Again, you can say the compiler can actually guess based on profiling. Maybe the compiler profiles the code, and for the input sets it profiles, this branch is 100% not taken, right? And 0% taken. And the compiler can optimize the code assuming this path, right? And actually existing compilers do that. They assume some path in the control flow graph. This is the control flow graph of a program. And optimize the code along that path. Of course, they need to provision such that if the code really doesn't go through that path, if the branch is once taken over here, then correctness needs to be maintained, right? Otherwise, you'll get incorrect code execution. So what the compilers do is actually add some fix-up code. So the code increases. So you have some fix-up code that fixes up the data values if the execution actually deviates from the optimized path. Does that make sense? So we'll talk about this when we talk about static scheduling. But that's the idea. Compiler can do a lot of different things. And this is used in GCC, for example. If you do, this is one of the ideas of super block optimization. And when we talk about static scheduling, again, we'll talk about that. But this is, at least a particular form of this is called a super block. Basically, the idea is you combine multiple basic blocks in the control flow graph into a super block and optimize that super block code. But whatever is outside the super block, whenever it needs to get executed at runtime, you need to execute this fix-up code to run correctly. OK. So hopefully this gives you an idea of the difficulty of doing static scheduling. Dynamic scheduling is nice in the sense that hardware does all of this, right? Hardware knows whether this branch is taken or not. Or actually, even though it may not know, it's predicted the branch. Well, we'll get to that. We'll get to branch prediction. OK. So how can the compiler alleviate this? Well, estimate the unknown profiling, which I've discussed. Actually, there are other ways when we'll talk about branch prediction. We'll see that profiling is one way, but the compiler can analyze the code also. Maybe if the compiler can analyze the code here, it may also think that most of the time this branch is not taken. Right? Let me give you an example. If you're checking an error code, for example, or if you have an assert in your program, how many of you program with asserts? Good. That's good style, actually. These are basically invariants that need to be correct, at least from your point of view, such that the program is executing correctly. Right? In a program that's executing correctly, that's written correctly, hopefully you won't go into error codes. For example, whenever you allocate some array, you check whether it's null or not, right? Value. And if you're trying to dereference a pointer that's null, you actually hopefully throw some error. Right? And in a normal program, you would expect that is not executed often. Right? In a normal program, you would expect that if p is not equal to null, well, I cannot write is not equal to null, right? This is the path you would expect to execute, else like throw error. In a normal program, you would expect that this is executed and this is rarely or almost never taken. Right? And the program compiler can analyze this error paths in the program and say, oh, this branch is not going to be taken. Right? It doesn't need to profile the program to actually decide this. That's another way how the compiler can alleviate the unknown, if you will. Okay? That's called program analysis. So maybe we should add profiling / program analysis over there. Okay. I think let's take a 3-minute break here, and we'll talk about control dependence handling. Do you prefer 3 minutes or 5 minutes? 5. Let's do 5. Okay. So that finishes up data dependence handling, but we're going to get back to it without order execution. So let me cover control dependence handling. It's another of the fascinating topics that has occupied architects for a long time. And this is going to cover, I'm going to cover it in multiple lectures. I'll introduce some concepts today. We're going to focus on branch prediction later on and some other ways of handling branches. Perhaps, I'm hoping by the end of the last lecture we'll be done. But if you scream and stop me, then I know that I'm going too fast. OK, review. Basically, the key question we're going to try to answer is, what should the fetch PC be in the next cycle? Right. Well, the answer is obvious, right? It's the address of the next instruction. But how do you determine that thing? This is actually a review slide. If the fetch instruction is the non-control flow instruction, it should be the address of the next sequential instruction. And it's easy to determine it if you know the size of the fetched instruction. But if it's a control flow instruction, then we have a problem. How do we determine the next PC? In fact, how do we know whether the instruction that we fetched is a control flow instruction or not? Right. I've already covered all of these questions. So we're going to try to answer some of these questions here. Oh, that's a really bright blue, bright yellow for some reason. It doesn't look like that. So there are a bunch of different branch types: conditional, unconditional, calls, returns, indirect branches, register indirect branches. And some of them, we know the direction at fetch time. Conditional branches, we do not know the direction at fetch time because they're usually dependent on registers, right? A computation on some registers. But some of them are always taken. Well, these are always taken. That's good. You don't need to predict which direction you will go. You just need to predict the target in this case, right? Target address. And the other question is, how many possible next fetch addresses do you have? For conditional branches, it's either the target, computed target, or the next sequential instructions address, PC plus 4 in MIPS. Unconditional and call instructions, actually they have only one next possible fetch address, so that's nice. These are easier to handle, as we will see. Return instructions actually have many potential return addresses, right? Because a call they could have many calls. There could be many call sites to the same function, right? Indirect branches also have many possible next fetch addresses. And when is the next fetch address resolved is a key question also, because this really determines how many bubbles do you have in the pipeline. Conditional branches, they're resolved after execution because you determine the branch condition based on a register usually. Unconditional branches, if you have PC plus offset branches, and that's going to be my assumption at the decode stage. So these are actually less important, if you will, because you can resolve them right away. Return and indirect, they're also resolved at execution. So we're going to try to handle all of these branches. But the most common ones are really the conditional branches, because you usually program structures such that you usually check some condition and do something based on that, right? And these happen a lot. So people have tried to optimize this a lot. But all of these actually disrupt the pipeline flow from the very beginning of the pipeline. So how do you keep the pipeline full with all of these instructions, when these instructions can disrupt the pipeline flow? Basically, we'd like to keep the pipeline full, and let's cover some potential solutions until we get to branch prediction. One option is not nice by now you know this. Stall the pipeline until we know the next fetch address. This is going to be terrible. You can guess the next fetch address while you're fetching this instruction. This is called branch prediction. You can employ delayed branching. Remember I mentioned this. You can change the semantics of the branch instruction such that branch takes effect after n instructions. Let's say you always execute the next instruction after the branch. Well, the reason that exists is because you want to keep the pipeline full. Right? If you change the definition of the branch such that the branch takes effect after n instructions, well, now you have n instructions to keep the pipeline full with. Now you got the reason, right? Do you remember? This was, I don't remember which lecture this was in, maybe lecture 2 or so, or lecture 3 or so. But I told you that we would get back to this. We'll cover this. You could do something else. This is my favorite solution because this could apply to pretty much anything, almost. You can get rid of all the dependencies by doing something else, or fine-grained multi-threading. I'll cover this in a little bit more detail. You could eliminate control flow instructions, which we will talk about. You could do predicated execution, which the ISA you're implementing actually has. It's called conditional execution in ARM, but it's the same thing as predicated execution. This way you can get rid of the branch instructions. Or somebody suggested last time you could fetch from both possible paths, right? If you know the address of the both possible paths, of course. This is called multi-path execution. And you could execute those paths and pick the one that's correct in the end. And we'll see advantages and disadvantages of this. So let's start with the bad solution. Bad but simple, I guess. Basically, stall the fetch until next PC is available. Is this a good idea? Who says yes? You can say yes. Again, it depends, right? Depends on what your design point is. If you want a slow processor, maybe it's a good idea. Yes?
I mean, if you want to have a very simple instruction set, you could set it up so that wherever you're branching to, maybe you're branching to the value in a register, and then as long as the compiler guarantees that that register is valid many instructions before the branch, then you're not going to stall, because you would know the address right away just by looking at the register value.
Assuming you could do that, yeah, that's right. And people have tried to propose those solutions. It's like prepare to branch instructions. Some IBM ISAs actually had that. You basically generate the register much earlier than the branch. And ideally, you would like to do that, and then you can just access the register file and get this. But you still need to have some time for the register file access, right? Maybe you do that early also in the pipeline. But I agree, that's a good solution. But it's usually difficult. Usually what happens is you do some operation, and based on that, you determine the branch condition. So this is also dependent on the program semantics. The key question is, can you actually separate that branch condition determination operation from the branch enough cycles ahead? And that's that's a very similar problem of can you find independent instructions to fill that distance? Okay, stall fetch until next PC is available. Good idea. Well, this is what the pipeline would look like in that case. Meaning you have a bubble every other cycle, because the next PC is really available at the end of the decode stage, right? Because that's when you know whether an instruction is a non-control flow instruction or an unconditional branch instruction. And this doesn't even take into account branches yet. This is assuming that you have non-control flow and unconditional branch instructions. That's a bad idea. Right. Okay, so how do you do better? Let's take a look let's do some calculations. Rather than waiting for the true dependence on the PC program counter to resolve, just guess next PC is equal to PC plus 4, such that you can keep fetching every cycle. Right. Is this a good guess? Well, let's take a look. This is what people have observed empirically for many ISAs. 20% of the instruction mix is the control flow instructions. 80% is non-control flow, which means that for those 80% of the instructions, this is really good, right? You predicted correctly. So 80% of the time, you predicted correctly. And people have also, these are ballpark numbers, found out that 90% of the backward control flow is taken. Backward means branch looks like this. The target of the branch is earlier than the branch in terms of instruction address. That's basically, these are loop branches. These are called loop branches. And 90%, this is empirical, of these are actually taken. Well, why usually people write loops that execute many, 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 many times, right? Think about adding 1 to an array that has 1 billion elements. 1 billion minus 1 times that loop will be taken, right? Okay. But forward control flow looks like if then else. So basically you have if do something, else do something. Basically you have a forward branch in this case. And in that case, people have empirically observed that that's about 50% taken. So this is more of a hit or miss. So a good prediction, think about this. If you see a branch like this, maybe you always predicted taken, right? But we're going to examine that simple. Always predict next PC is PC plus 4. And overall, people have found that, researchers have found that typically branches are about 70% taken and 30% not taken because loop branches dominate execution. Okay, so if you actually say next PC equals PC plus 4, 86% of the time you would be correct. I could have asked you this question, but I've done the calculation. Why is the 86% time? Because 80% of the instructions are not branches, which means that this is true 80% of the time. And among the remaining 20% of the time, 30% of the branches are not taken. 20% times 30% is really 6%. So 80 plus 6% is 86%. So 86% of the time you're correct. 86% of the time you're fetching, you're correct. So that maybe that's a good idea to start with, right? But we're going to try to do better. Because if you actually have a pipeline, this 14% is losing a lot of performance. And let's take a look at that actually. Okay. Actually, we'll take a look at that. We're going to try to make this more effective. But one question before we move on. Assuming this is the case, the idea of guessing next PC equals PC plus 4, always predict the next sequential instruction is the next instruction to be executed. That's a form of next fetch address prediction and branch prediction. Very simple, very primitive form. Right? But it buys you a lot of things. Maybe it's not as effective, but how can you make this more effective? Any ideas? You have a, yeah?
You make the branch taking code the next code that you execute.
Exactly, yes, exactly. Basically maximize the chances that the next sequential instruction is the next instruction to be executed. And you can do this in software. The compiler can lay out the control flow graph such that the likely next instruction is on the not taken path of a branch. And this is really easy to do if the compiler can profile, right? Or can think. Basically, I'll draw this control flow graph. You have a branch over here. This is the taken, this is the not taken. This is basically PC plus 4 after the branch. If the compiler knows that, let's say it profiles the code, it figures out that 99.9% of the time the branch is taken. And 0.1% of the time the branch is not taken. What the compiler can do is simply change the target, right? Lay out the code such that the not taken path becomes the taken path, and taken path becomes the not taken path. Right? That way, 99.9% of the time this branch is not taken, but the hardware has this prediction mechanism, which is now much more effective. Right? Does that make sense? So basically, here you're relying on the software to make the hardware prediction much more effective. And this is actually a neat idea, I think. People have, existing compilers also do this today. A lot of the company compilers, Microsoft and Intel compilers, as well as GCC does this. But this idea, if you want to read more about it, there's a really nice paper by Pettis and Hansen. It's called Profile Guided Code Positioning. Now you can actually understand the title, right? Profile Guided Code Positioning. It basically says what I described to you. Based on the profile information, you guide the code positioning, where the code is laid out. And this is a paper in PLDI, Programming Language Design and Implementation, in 1990. This is an old concept. Okay, it's beautiful, right? This is one example of where you have a hardware mechanism and you design the software to take advantage of that hardware mechanism to make it much more effective. Maybe this is food for thought for you. How can you actually do this in hardware? Can you make this code layout transformation in hardware? And I will say that you could actually. There could be ways of relaying out the code just purely in hardware without exposing it to the software, such that you make this more effective. I'm not going to go into detail, but one example that looks like this is the trace cache, the concept of a trace cache. We'll see if we're going to be able to cover it this semester. But this was implemented in Pentium 4. But Pentium 4 trace cache, what they did is they cached the instructions this way. They basically put the instructions that are commonly executed in a sequence into a special cache, regardless of where, commonly executed, frequently executed paths in a cache, such that you're always going through this path that is frequently executed. That way you don't even need to predict, right? Assuming you're always following this path. Okay. Ignore this if you didn't understand it. But this is something that's, so existing processors, this is to show you that existing processors try to optimize this branch, to try to ensure that you're fetching from the correct path with very different mechanisms. Right? You could do this in software or hardware. Okay, how else can you make this more effective? Well, you can get rid of control flow instructions, right? Because this is nice if all of the code is sequential. And if you get rid of the control flow instructions, everything is sequential. It's beautiful. Or minimize their occurrence. I guess a good exam question could be, can you get rid of all control flow instructions? Maybe you'll think about that. How can you do this? Well, one is get rid of unnecessary control flow instructions. Basically, maybe you have some unnecessary control flow instructions, and I'll talk about that. You can combine predicates. Instead of testing every time, you may have complex predicates. You may have a branch testing complex predicates. You can convert this into multiple branches or a single branch, right? Single complex branch. Let's take a look at that right after this slide. The second is what ARM enables you to do conditional execution, predicate execution. Convert the control dependencies into data dependencies. Right? And we'll see an example of this also. Let's look at predicate combining first. This is not predicate execution. Predicate execution is this. Predicate combining is get rid of unnecessary branch instructions. So let's take a look at this code, this piece of code. If you look at this, there are 3 conditions that are tested here, right? And if all 3 are true, then you're going to execute this code over here. The compiler has a choice here. The compiler can convert this into 3 conditional branches, test this condition. If it doesn't hold, jump somewhere. Test this condition. If it doesn't hold, jump somewhere. Test this condition. If it doesn't hold, jump somewhere. And these are nested test cases, nested branches. Or you could do computation. You could compute all of this without doing any testing, and at the end have a single branch. If the entire thing is true, jump here. Otherwise, go to the fall through path. Basically, the compiler can compile this into 3 conditional branches or 1 conditional branch. And the idea of predicate combining is compiling this into 1 conditional branch. Make sense? You combine the predicate operations to feed a single branch instruction instead of having 1 branch for each predicate operation. Predicate operation is basically the operation that determines the condition of the branch or condition of a control flow. Of course, predicates can be stored and operated on using condition registers or any general purpose register, right? You can do all of this computation on general purpose register. And eventually, this single branch checks the value of the combined result. The upside, now you have fewer branches in the code. And the hope is that you have fewer mispredictions and stall. You can always go through next PC equals PC plus 4, except when you hit that branch. Is there a downside for this? Yes?
Does that break short-circuiting?
Yes, exactly. Basically, this is what you mean. Possibly unnecessary work. Which means that you don't really need to, for example, test this condition or even compute this condition if this condition is not true, right? If A is not equal to B, then you don't need to execute all of this. Whereas if you combine the predicates, well, you have to execute all of this to determine whether or not you need to branch. So you get unnecessary work. And this is true whenever you want to eliminate branches. Whenever you eliminate branches, you are bound to do some unnecessary work, unless your program is heavily unoptimized to begin with. Okay, so specialized condition registers actually exist in many architectures. But this is the idea of combining predicates. It's simple, right? You do it in your programming too, probably. I mean, you could actually do if, else, but that may not be converted into real branches in the end. If a compiler is smart, it looks at opportunities to combine branches and combines them. Right. Okay, let's look at predicate execution, which is different from what I just discussed. The idea here is to convert the control dependence into data dependence. And the simplest form of this is, well, you're seeing this in ARM, right? You have every instruction has this condition field. An instruction executes only if that condition holds, right? That's the idea over here. But many ISAs actually don't have this predicate execution. Suppose we had a conditional move instruction. And the idea is this. Conditionally move register 2 into register 1 if this condition holds. And this could be, this is basically the specification of the instruction. If the condition is true, register 1 gets register 2's value. Otherwise, register 1 gets register 1's value. Have you guys used this C operator? Okay. This is not unfamiliar. It's not familiar? Okay. This is basically how you would do exactly this in C. You basically have a condition that you test. If that's true, this operand, this is executed and assigned to this. If that's false, this is executed and assigned to this. That's basically the C statement. And this is employed in most ISAs, most modern ISAs actually. x86 has, even though it doesn't have full predicate execution, just like ARM. Well, ARM has full predicate execution. It doesn't have x86 doesn't have full predicate execution. It has this conditional move instruction. Let's take a look at a code example with branches versus conditional moves. So let's say we're trying to do this. I don't know if oh, there you go. That's what I was looking for. Basically, if A is equal to 5, B equals 4. Otherwise, B equals 3. And then you may have something here, unconditional match here. But you can test branch equal A equals 5, right? This is what the control flow graph looks like. And this is what the conditional execution looks like for this predicated execution. So the downside of this is now you have a conditional branch here. Whereas with the predicated execution, you have 3 instructions. I'm not going to write the same thing over here. But you basically have a compare equal instruction that compares A and 5 and sets the condition if they're equal. You have a conditional move instruction. If the condition is true, it moves 4 into B. And you have another conditional move instruction. If the condition is false, it moves 3 into B. Does this make sense? So you can implement this in 3 instructions. Is this interesting? Or?
Yeah.
Yeah. Why is it hard? Or?
No, it's
okay.
fine.
Okay.
It's not bad.
Okay. Okay. I thought there was something wrong in the slide or something. Okay. Yep. Basically, you could do this in x86, which doesn't have predicated execution, but this is a form of predicated execution, as you can see. You can. I think you can do this in ARM also, right? By now. So what is the benefit of this? The benefit is now this is straight line code, right? There's no branch inside here. It's all straight line code, which means that next PC equals PC plus 4 works perfectly. You always get perfect prediction. Again, the downside, unnecessary work. Right? One of these is unnecessary because you're conditionally executing an instruction. Right? You don't have to do that. You didn't have to do that if you predicted it correctly. Right? If your branch prediction was correct, you would just execute the code that you really need to execute. Okay. Well, we've already talked about this. And we're going to get back to this, actually. But let me give you advantages and disadvantages of this. This eliminates branches, as I've shown you here. It enables straight line code. Or you can think of it as larger basic blocks in code. Do you know the definition of a basic block, by the way? What's a basic block? 213 should have covered this, but maybe not. No? Okay. A basic block is a block of code in a program that has a single entry and single, well, I guess when you enter it, you execute all of the instructions. Let me put it that way. Does that make sense? Or a single entry and single exit point. Single exit point is this instruction, single entry point is this instruction. Make sense? Once you have predicated execution, you're enlarging the basic block. The entry point and exit point and the number of instructions over here becomes larger, right? Whereas if you look at a control flow graph that looks like this is another basic block. 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 Right? You have piece of code that has a single entry point and single exit point. Why do you want larger basic blocks? Well, because of one of the reasons is what we've discussed, right? Because it's straight line code. You don't go somewhere else in the middle of the basic block. Then it'll be a different basic block. Okay, this basically increases straight line code. And there are several advantages to this. One of them I've already given you. Always not taken prediction works better. No branches. This actually helps compiler also, right? Remember, I had somewhere, compiler needed to profile over here. Whereas if the code is this way, the compiler now has more freedom to optimize the code, right? It knows all the data dependencies. It doesn't need to figure out, oh, this branch goes this way, this branch doesn't go this way. That branch is gone now. Right? The compiler has perfect knowledge of the potential data dependencies here, except for memory addresses. It can reorder the code freely, much more freely within this large basic block. That's one other advantage of predicated execution. Okay, I think I've already told you this. What about disadvantages? I think I've already given you this one, right? Whenever you eliminate branches, you do some useless work. Some instructions are fetched and executed, but they're discarded. And these are instructions whose conditions evaluate to false. Right? Now this could be bad for branches that are easy to predict, and we will get back to this. If for example, this is really easy to predict, 99.9% of the time you're going this way, only 0.1% of time you're going this way, somebody suggests that you turn this into a predicated branch, a predicated execution. Right? Which means that you're combining this block, this block, this block, right, and this block with conditional execution. Now the branch doesn't exist, everything is straight line code. Is this a good idea? No, right? Very likely no, because you really need to execute this 0.1% of the time. Now if you combine them in predicated execution, you always need to execute this. Now again, it depends is the right answer actually. I think you said it depends with your gesture. That's right, it depends. If this is really, maybe one instruction only, maybe it's worth it. Right? Maybe it enables optimization opportunities across here. But if this is 100 instructions, maybe it's not a good idea because you're executing 100 instructions all the time, except you need to execute them only 0.1% of the time. But it depends is a good answer. Okay, requires additional ISA support. Obviously, right? Conditional execution in ARM, for example, needs to have the condition fields. Yes?
No.
No? Okay.
Backwards branches, unless you want to write them all out.
That's right. Exactly. Exactly. Can you eliminate all branches this way? No, you get the point for the exam. You cannot. Because if you have a loop branch, how do you do this, right?
Well, you could just iterate through your entire memory space, but
Yeah, that won't. That may not be very efficient, right? Yes. Yes.
Couldn't you use the conditional move to move backwards?
Uh-huh.
And that's not. I guess it depends on how you define it, whether conditional move is a branch or not.
well, you'd have to conditional move into PC, which
That's
is
right.
a branch.
Exactly. Yeah, that's right. I'd be curious if you have a solution, but this is a very tough problem. Okay, we'll get back to this. So there are some readings. This is the seminal paper, actually, that introduced predicated execution, conversion of control dependence to data dependence. Again, the title says the entire thing, right? It's in Principles of Programming Languages. And this is actually a paper that we wrote that makes predicated execution much more effective and useful by combining it with conditional branching, called it the wish branches. And we'll try to get to it. Okay, let's see if we have time to cover delayed branching. Maybe we should stop here. And even though we haven't covered everything I wanted to cover, did I go too fast? Or it was good or fast? It's good to get this feedback before we leave. What do you guys think? Who says it's good? Good pace. Okay, that's it. Who says it was fast? Okay. It was what?
Good and fast.
Good and fast. Oh, okay. Well, these are two different dimensions, actually. I didn't mean for the good part, the content may be good, but the pace, was it slow? I guess I should ask slow or fast. Okay, it wasn't slow. Okay. Who said it was too fast? I didn't understand anything. Okay, we'll try to go a little bit slower next time.
I think my feelings are it was fast enough that we got through more materials,
Uh-huh.
even though I didn't necessarily get every bit
Uh-huh.
of it. I got more overall than I would
I
have
see.
if we had gone slower.
Okay.
So,
Okay, that's good. Yeah, that's always a trade-off.
right.
And sometimes I expect you guys to actually do the reading and learn more. Yes?
Yeah, I feel like if I was to have an interview on this stuff, I could throw around a lot of keywords and sound really smart, but if you actually ask me to like draw something, I'll be moved.
Sure. See, that's why you need to implement your lab and study this afterwards. Okay, I'll see you on Monday.